Hello, welcome back. Let's look at subsection 3 of 5.2, which is called least squares solutions. Now, this is going to turn out to be really similar to what we were doing before. We're just going to look at the problem of finding projections in a slightly different way. So, the way we were finding projections before is when you have an orthogonal basis of the subspace, like everything in W can be written as a linear combination of this orthogonal list of vectors. But what if we just have any old vectors, A1 through AC, that we put in a matrix and call the matrix A? So the span of those vectors is also known as the column space of A. Now, as we've seen all the way back in chapter 1 and 2 and everywhere, like if your y is in the column space, then finding a solution of ax equals y is possible. There is a way to write y as a times x. But if you have a vector y over here that is not in the column space of A, meaning it is not able to be written as a linear combination of the columns of A, then maybe we can get ax to be as close as possible to y. So we're not actually solving ax equals y because it has no solution. But we can say that ax equals y has a least squares solution. The least squares solution is x hat, which is the scalars that you scale the columns of A by to get to this point as close as possible to y. Now, we know from theorem 5.8 that says there's projections exist and they're unique, that there is a y hat point here that makes it so y minus y hat, minus a x hat, is orthogonal to w. Now the trick to finding the least squares solution, the scalars you multiply the columns of A by in order to get to this point as close as possible, is to use theorem 5.6, the four related subspaces theorem from the last section, which says that the orthogonal complement of the column space, the set of vectors orthogonal to the column space of A, is the null space of A transpose. In other words, if this vector here, if it's orthogonal to the column space of A, it's in the null space of A transpose as well. So that means if you do A transpose times that, you're going to get 0, because that's what the null space of A transpose means. It means vectors you can do A transpose times and get 0. So then, if you just distribute the A transpose over this, you get A transpose y minus A transpose times A times x hat equals 0. And just moving things to the other side, you get this is equivalent to A transpose A x hat equals A transpose y. So we know that this A x hat exists and is unique, but that doesn't mean that x hat is unique, because there might be more than one x hat that satisfies this equation. Because remember that we don't know that the columns of A are orthogonal. We don't know that they're even linearly independent. Now, the theorem over here says that if A did have orthogonal columns, then they would be an orthogonal basis for the column space of A, and we would have these unique things. This would be like the x hat components here. But we don't have that. So there might not even be unique least squares solutions. There might not be a unique x hat. So yeah, so this proves that least squares solutions exist. So if you have any matrix and y is a vector in RR, then A transpose A x hat equals A transpose y if and only if A x hat is the projection onto the column space of y, which is the closest point in the column space of A to y. That makes the distance from y to that orthogonal projection smaller than the distance to any other point. Now we call this x hat the least square solution of this equation because it minimizes the distance from y to ax hat, and the distance formula is a sum of squares. So that's why it's called least squares, because you're minimizing a sum of squares. Okay, so that's the gist of this. Let's do an example. So in the first example, example 1, we found that if A is E1, E2, well, of course, the column space of A is just the x1, x2 plane, and we found the projection of y onto the x1, x2 plane. Let's check that if we do it using this theorem, this formula here, we get the same result. So we're going to try to solve this equation, A transpose A x hat equals A transpose y. That should make A x hat equal to this projection, which should be 4, 5, 0. So let's try it out. So A is just 1, 0, 0, 0, 1, 0. We're multiplying that by A transpose on the left, which has rows 1, 0, 0, 0, 1, 0. And we want to get x hat times that equal to this A transpose times y, like so. And we just got to multiply everything out here. So this is a 2 by 3 matrix times a 3 by 2 matrix. It's going to end up being 2 by 2. And using the row column rule here, you'll just get 1 here, 0 here, and column 2, we'll get 0 here, and then 1 down here. So that just gives you the identity matrix, which is nice. And then 4, 5, 6 times this thing is going to be 4 times 1, 0, 5 times 0, 1, plus 6 times 0, 0. So that's just going to be 4, 5 when you simplify that. And this just is already in reduced row echelon form. The solution for x hat is just 4, 5. So in this case, there is a unique least squares solution. It's not always unique. It depends on the matrix A that you have. It turns out the columns of A have to be linearly independent to guarantee a unique least squares solution. And they are in this case. So that's the least squares solution, but A x hat means doing 1, 0, 0, 0, 1, 0. That's the A times this 4, 5, which will give you 4, 5, 0, which is indeed the projection onto the column space of A of y that we found before. Sounds good. Let's do a trickier one here. So now we're trying to find the least squares solutions to ax equals y. Now remember, what this means is that ax equals y might not have a real solution, but we're trying to get as close as possible to get a times x hat as close as we can get to y. That's really our goal here. And the way to do that is to make ax hat be the projection of y onto the column space of A. And we saw how to do that using this theorem. We need to solve these equations with the A here that we've got. So the theorem says we need to solve A transpose times A times x hat equals A transpose times y, and that's guaranteed to have a solution. And let's work that out. So first of all, I'm going to write the A x hat. Actually, let's move this to the left to give ourselves more room on the right. Here's A transpose, turning the columns of A into rows of A transpose. All right, so we need to multiply all this out. We can use the row column rule for that. That's what I got for doing A transpose Y. I feel like maybe I should check this with a computer real quick. Oh, I did make a mistake here. This should be -1. Everything else looks good. And by the way, sneak preview for what we're doing later. This is a symmetric matrix, A transpose times A. It's equal to its own transpose, right? So now we can row reduce this. I'm going to start by scaling row 2 and moving it to the first row. So that will be 1, 2, 3, 3. And I'll leave the other rows alone. Then we can clear the 6 and -7 by adding multiples of the first row to rows 2 and 3, leaving row 1 alone. And at this point, I notice row 3 is a multiple of row 2, which means adding 2 times row 2 to row 3 to replace row 3 will completely eliminate row 3. So we can do that. And I'll also scale row 2 to get it into reduced echelon form. We still need to get rid of that 2. All right, so this now has an infinite number of solutions because we have a free variable in the x3 column. So using the normal method, we can solve for all of the variables in terms of the free variables. And x3 is just x3. So this gives us an infinite number of least squares solutions. It turns out there's an infinite number of them because the columns of A are not linearly independent. So one example of a least square solution is if you just let x3 be 0. That just gives you 1, 1, 0. And we can find the nearest point of the form ax to the vector y by just doing a times this 1, 0, 0, which will just be 1 times the first column plus 1 times the second one. That'll be -1, 2, 3. And yeah, that doesn't seem too far from y hat. Again, the least squares is the distance from y to column A, and that will be the magnitude of y minus ax hat minus that projection, which will end up being the square root of 5, I believe. So the square root of 5 is the closest you can get if you're in the column space of A to the vector y. All right, so that is projections and least squares solutions. Good luck with the basic homework, and I will see you later.